several kilograms of your body is bacteria, probably somewhere between 10 and 15 kilograms of your body is bacteria. But they number far more than the other cells of your body, and you could not exist without them. Those bacteria, everywhere we look on Earth, every natural place that we look, 20 kilometers underground, in the deepest ocean, underneath glaciers, in the stratosphere, there's life everywhere. It's not life like you and me, but it's mostly bacteria. And there's a there's a category that we talk about when we discuss life that lives and thrives and exists in extreme environments that are too hostile for you and I. We call those extremophiles. And it turns out, if you look at the biomass that is encompassed by all the extremophiles on Earth, the ones deep underground, in the deep ocean, their biomass outweighs the rest of the living organisms on Earth. Also, if you look at Earth history, you find that bacteria, extremophiles, have dominated life throughout Earth history. And these extremophiles are really bizarre creatures. This is a few pictures. Some that live in the deep ocean, under 4 kilometers of water. Some things that look like aliens themselves. That's a methane ice worm. It lives in methane ice clathrate at the bottom of the Gulf of Mexico, 2 kilometers deep. And there are bacteria that live in the ground underneath us. You could go down 5 kilometers, bring up rocks that haven't seen sunlight in hundreds of millions of years, and there would be bacteria there that are going through their life cycle. They're as happy as bacteria can be. Now, some of them are ugly. This one here is called a tardigrade. I have a little bit more to say about tardigrades in a minute. But we find these extremophiles in a wide range of conditions. We find them in below the freezing point of temperature, say below 2 kilometers of ice and glaciers. We find them at high temperatures, above the boiling point of water. We find some that exist over the entire range of pH on Earth. These are some of the categories: psychrophiles, mesophiles, thermophiles, hyperthermophiles, acidophiles. Remember that word, because acidophiles are organisms, bacteria, that like to live in acid. I mean, think about that. They live in acid. Then there are alkalophiles that live in an alkaline environment. And then there are many subgroups. There are some that live only in the deep ocean, barophiles. There are some xerophiles that really can't tolerate water, of all things. And there are indolents that live inside of rocks, and toxitolerant bacteria that live in toxic environments, like an environment that's all carbon monoxide, which again is poisonous for you and I. And then there are some things that are more than just bacteria. The tardigrade, as I mentioned earlier. This is a picture of this ugly little creature. And you can see them with your eye. They're between like 1/10 and 1 millimeter in size. But they're amazing. You could freeze them, keep them frozen for weeks, thaw them out, and they're happy. You can dry them up, let them just dry out completely for years. Add water, and they reanimate. You can put these things in a high radiation environment that would kill you and I in minutes, and they're fine. They can live without water, without oxygen. They can live in boiling alcohol. I don't know if you ever thought to do that experiment, but living in boiling alcohol. It's amazing how adaptable life is. Now think about that, because we see a lot of strange environments in the universe. This tells you that life can adapt to a lot of strange environments. Okay, what about the Earth itself? What can we say about the Earth? Not just life on Earth, but how it's changed over time. Well, we know that how old the Earth is. We can define the age of the Earth to at least 3 significant figures: 4.56 billion years old. At that time, the Earth came together from a bunch of asteroids and protoplanets, and it was a magma ball. It was just molten rock from the center to the edge. But as soon as it cooled off, and a few comets sprinkled water here, there's evidence that life was present. And not just present in a few places, it was present ubiquitously over the surface. So we don't know what the origin of life was, but we know that it had to be robust. It happened so quickly. We know that that life has changed with time over 4.5 billion years, or 4.2 billion years, and it has changed the environment as the environment has guided its evolution. And, take a breath. The oxygen and nitrogen they're breathing is a product of photosynthesis and nitrogen-fixing bacteria in the soil and denitrifying bacteria in the soil, and things that happen in the ocean. So there's been a coevolution of life and the Earth for 4.2 billion years. And again, life is extremely hardy. So, recap on this section, life on Earth needs the three things: liquid water, usable energy, raw materials, carbon. The Earth has been an extreme environment for most organisms, now all the way back to its beginning. The first form of life on Earth was almost certainly an extremophile because of its extreme environment. And most life on Earth now is a type of an extremophile, some type. And they can survive, as I said, in amazing conditions. So, given that, what can we say about habitable places in our solar system? Now, it wasn't that many years ago, when I was a kid, that the view was that the solar system had no water elsewhere on Earth. And the few pictures we had from like the Mariner spacecraft to Mars and Venus showed that they were dry and deserts, and they didn't look at all like that they would be habitable. But that has changed. Now we have a pretty good idea that life as we know it, again, there may be other types of life that we don't know, but sticking with the kind we do know, is probably only going to be found on planets. The stars are too hot for the biomolecules to be stable. Asteroids and comets are too cold to have liquid water. But planets are amazingly suitable for life as we know it. I mean, that's astonishing if you think about it, that if you were going to create a universe, you would want a factory to generate complex elements that then were distributed throughout the galaxy to form planets that had a wide mix of elements and usable energy. And this is what we have. It's astonishing. So we're going to look at planets. We're not going to look for life on asteroids or on the sun, not ruling out the possibility it could be there. Okay, so a 1-minute introduction to the solar system. And this is the way you typically see it in a textbook. The sun in the center. You have 4 inner rocky metallic planets. The Earth is one of them: Mercury, Venus, Earth, and Mars. You have the giant planets, Jupiter, Saturn, Uranus, and Neptune, that are out beyond the Earth-like planets, beyond the asteroid belt. You have, the asteroid belt, a few million rocky, metallic, carbonaceous objects between Mars and Jupiter. You have Pluto, which is a member of the Kuiper belt, which is about 100,000 dwarf ice planets. Let me pause. Just thinking about the resources in our solar system and what humanity needs to move into space. There are enough raw materials, water, metals, carbon, the things in our solar system among the asteroid belt and the Kuiper belt and the comets to provide the needs of of humanity for millions of years. Can you imagine how that all comes from just a few simple laws of physics and hydrogen? So this is our solar system, and again, the things we want to focus on are those things, those places that will provide the things that we know life needs. We'll start with liquid water. These are the places that have liquid water in our solar system that we know of. There are probably other places. We've got the Earth, but then there are 3 moons of Jupiter. If you were looking at that planet now, 3 of those 4 moons each have more liquid water underneath an ice crust than the Earth does. Earth is one of the drier places in the solar system. And there are other moons. Titan is a moon of Saturn. And then you've got Triton, which is a moon of Neptune. They have liquid water too. Even Pluto, 30 times further away from the sun than the Earth, it has an ocean of liquid water. So now, we don't have time to go through all of these, but I'm going to give you 3 examples of places that are habitable. But keep in mind, remember, there are many such places that are habitable for the dominant form of Earth life. Okay, so Venus. Venus has been in the news lately. And I did a sort of a quick search to look at the headlines about the discovery of a molecule called phosphine in the atmosphere of Venus. Well, on the left is a picture of Venus. You don't see the surface because it has a thick atmosphere and is completely cloud covered. The atmosphere is all carbon dioxide, and the clouds, sulfuric acid mixed with water. You never see the surface because the clouds are so thick and so ubiquitous. It's constantly raining sulfuric acid, but not a drop ever gets to the surface because the surface is around a temperature that would melt my laptop in just minutes. It's so hot because of a greenhouse effect. The greenhouse effect on Venus is about 10,000 times the greenhouse effect on the Earth. And the one on the Earth is not trivial. Without the greenhouse effect on the Earth, it would be an ice planet, covered in ice everywhere. It's because of the greenhouse effect that we can live on it and have liquid water. But you can have too much of a good thing, and that's what Venus does. It is so incredibly hot. It's an acid environment. There is one place above the surface, about 70 kilometers high, where it's room temperature in the clouds, in the acid clouds. And interestingly, when that environment, that portion of the clouds, low pressure, room temperature, acid environment, when those are simulated in the laboratory, and you take one of these extremophiles called an acidophile, and you put them in that environment, they not just survive, but they thrive. So in a very limited sense, Venus is habitable. But otherwise, you would think it's incredibly hostile. So it wasn't even on that previous picture I showed you. Now, what happened was the discovery of this molecule. Of course, the headlines didn't focus on just that. It was, scientists discover potential life on Venus, and this is actually the picture from one of the news stories that I found about that. And it was intriguing. I won't go through all the details, but I want to explain to you the story. Phosphine is phosphorus with 3 hydrogen atoms bound together. It's a molecule that's very unstable in an environment that has oxygen. Certainly free oxygen would cause it to oxidize on a time scale of seconds or less. In the air around us, there's a little bit of phosphine, but it's constantly being produced by bacteria and being destroyed by oxidation. Venus has an atmosphere of CO2, carbon and 2 oxygens. It has a lot of oxygen that's cycling through the carbon dioxide, carbon monoxide, and free oxygen. So there was no expectation to find phosphine there because it was more oxidizing than the Earth is. But nevertheless, it was found in the atmosphere, in the cloud cover. Now, does that mean that there's life there? Well, phosphine, as far as we know, on Earth, is only produced by life. That is in the natural environment. You can do in the laboratory different things. But there might be other mechanisms for producing phosphine on Venus. Now, the study actually just focused upon the discovery itself and how much was there and the details of the observations. And the authors then went on to say, well, we can't explain why it's there. We don't think it's, chemistry. We don't think it's volcanoes. We don't think it's lightning. The only thing that we can think of, it might be life. And they left it at that. They didn't say that they had discovered life on Venus. It's interesting, but almost no scientist that I know thinks that it's due to life. It's intriguing. It's an important discovery. But it's not yet that discovery which tells us that there's life elsewhere. I know it's still in the news somewhat. And as I said, it's an important discovery, and certainly for our understanding of Venus. But it's not that. It's not that smoking gun yet. I want to move on. Let's go to Mars, okay? Venus, first example, Mars. Mars is the most Earth-like planet. In fact, if you were on the surface now, it would look like a desert. You could not breathe with without a spacesuit because there's no oxygen, or at least very little oxygen. It looks like a dried up Earth-like planet. It looks like a planet that once had lakes and rivers and oceans, and there's plenty of evidence that it was like that at one time. In fact, simulations show that Mars once had an ocean of liquid water that was at least 1 kilometer thick if you spread it out evenly on the surface. Of course, it cooled in the low areas, and it gave you oceans and seas, and there was a hydrological cycle. In fact, there's evidences that the water was even drinkable at times. There are giant volcanoes, though, that were active when Mars was once habitable, and so that probably changed the planet from a habitable to an environment that was pretty hostile to and certainly you and I, and maybe even most types of bacteria, but it was once habitable on the surface. That's the point. So the question that comes up, is it habitable now? Well, the surface, no. It's just too hostile an environment for any kind of extremophile that we know of. But, and this is a very important point, we've discovered lakes of liquid water underneath the surface of Mars. They're isolated from the surface. There are lakes that are dozens of kilometers long and a few kilometers thick that are sandwiched between rocks about 1 kilometer deep or so. We have not been able to study those yet, and we're probably not going to until we can do it without contaminating any of those lakes. But we've seen those lakes in just places where they could easily be seen. There may be thousands more like them. Also, the subsurface of Mars is habitable. Liquid water, carbon, room temperature, raw materials, anything you might need. It won't be creatures like this. This is what people once thought that Mars life would have to be like. A thin atmosphere, so it'd have to have big ears to hear. It would get cold at night, so a parasol that wrapped itself around it and kept it warm. Water, hard to find, so it had a long nose process that would have to go into the ground deeply to find water. That's not what we're talking about. We're again talking about extremophiles that are bacterial. If there's Mars life there, under the surface, which we know is habitable for Earth-like extremophiles, what are they going to be like? Well, one type is a bacteria that eats carbon monoxide, a poison, and produces methane as a byproduct. And sure enough, we have found methane plumes coming out of the interior of Mars. Does this prove that there's life underneath the surface of Mars? Well, no, it doesn't. But it's the kind of thing that we had our experience with Venus. Looking for a chemical that's produced by life is a good indicator that something interesting is going on. And this is probably the only way we know of to look for life on a different planet without actually going there. But it's not perfect. We don't know what this means. The scientific community is about split on this. I would say probably 3 to 2. 3 people think that this is probably not life. About 2 think that it is. But we don't know. We just don't know yet. We're going to have to go there, get some rocks, bring them back, and so on. The third example is one of the moons of Jupiter. Now here's a picture of Jupiter, the way it looks from a spacecraft, and I like to show this because it shows that when they say it's a giant planet, they really mean it. That's how big the Earth is compared to Jupiter. That's the scale. But Jupiter has a small system of moons around it. Only, the 4 of them that Galileo saw are just a tiny fraction of the moons that it has. But they are the largest ones. Io, Europa, Ganymede, and Callisto. And here is a little sliver from Galileo's notebook in 1610 where he drew the positions of each of those moons. He saw them. He figured out how far away they were from Jupiter, how long their days were, and so on. I don't think he ever imagined that they could be habitable. But, sure enough, 3 of these, not Io, that's volcanically consumed the surface. But the other 3 have oceans of liquid water. Europa has an ocean of liquid water underneath an ice crust. The ice crust is probably a few kilometers thick. The ocean underneath it is probably 100 to 200 kilometers thick, and there's more liquid water in that ocean than in all the oceans on Earth combined. And we're really interested in going there and seeing what's inside that ocean. So many of the plans for the outer planets focus upon what we call ocean worlds, places where there are oceans. Most of them are covered by ice, but we're going to have to go there. They do have plumes of water sometimes shooting out of them, but you can't be sure what's inside the oceans without going there. So there are going to be new missions you're going to hear about over the next decade or two. There are going to be landers on Europa, potentially drills or submarines that go into the ocean underneath the surface and look for samples of life. So a little cartoon to show you how Earth is one of the drier places. If you took all the liquid water on Earth, put it in a cube, you would make 1.3 billion cubic kilometers. Again, a big number. But look at the scale. Europa has at least that much, but we think it's more like 3. Titan, the moon of Saturn, 13. Callisto, at least a dozen times more water, and so on. When I was in college, this was the view. Venus, too hot, Mars too cold, but the Earth was just right for life. But the things I've been telling you about has completely changed. It's been a revolution in our thinking about life elsewhere. That is, we know of at least 10 places now. I just talked to you about 3 of them briefly. At least 10 places in our solar system where Earth-like life, not even considering the possibility that life could be different or evolved to those environments, Earth-like life can survive and probably thrive in at least 10 places in our solar system outside of the Earth. This is a few of them. Mars, Titan, Europa, Pluto, Enceladus. There's even an asteroid called Ceres in the asteroid belt, which is about 600 kilometers across, that we now know has a brine ocean, a salty ocean just underneath a rocky crust. And sometimes it has plumes that shoot stuff up and deposit salts on the surface. But these are all places that are ocean worlds and habitable. Okay, moving on. Life beyond our solar system. What are we looking at? Well, we're looking for planets, places that are habitable, and we're looking for signatures of life again. Now, it's hard to do. It's hard to find a planet, even one as big as Jupiter, close to a nearby star. If the sun was up, you wouldn't be able to see Jupiter. There's just too much contrast. And you take both of them and you put them 5 light years away, there's almost no hope of seeing Jupiter next to the sun. So it's hard, but it can be done if you use very precise techniques to look at when Jupiter goes in front of the sun and behind the sun, and you difference the light that you see. And so we've found lots of planets around other stars. In fact, just huge numbers of them. So many that every time I give a talk, I have to go to the Exoplanet Encyclopedia and check what the daily total is. Yesterday I checked, and it was 2 lower than what it is today. It was 4,360 yesterday. 2 planets have been discovered since yesterday. Our discovery rate of planets around other stars is about 1 per day. And within a few years, we're going to know of 10,000. Within a few years, we're going to have better techniques that there will be tens or hundreds of thousands of planets that are known. They are incredibly diverse. Now, this is a complicated figure. I'm not going to go through it. But there are Jupiter-like planets that are hot, and there are some that are cold. There are rocky planets. There are lava worlds, and there are planets that show mixtures. One side is lava, one side is water. Basically, if it obeys the laws of physics, there's a planet probably out there that you can imagine. So if you imagine a planet, and again, if it obeys the laws of physics, it's probably out there. If there's a 1 in a million chance that it's around a star, that means that there's over 1 million of them in our galaxy alone. How big are they? Well, this is a histogram showing how big the planets are compared to the Earth. So here's Earth-sized planets right here. Most of them are somewhere between Earth size and Neptune size. In other words, a few times the size of the Earth. So the Earth is sort of a small planet compared to the other planets. And many of them are habitable. Again, information is still sketchy. We have to be a little bit careful. But there are about 60 of these planets that we have now been able to say that are at least as habitable as the Earth for the dominant form of life on Earth, or, and this is a kicker, they're more habitable than the Earth. Now that's something that's relatively new. How can something be more habitable than the Earth? Well, it turns out that the Earth now is not as habitable as it was 200 million years ago. 200 million years ago, it was warmer, there was no ice caps, there was an ocean pole to pole, and there were rich carboniferous forests all over the place. And of course, dinosaurs and other critters. The Earth was more habitable, more biomass then than there is now. Many of these planets are more habitable than the Earth. Is there life there? We don't know yet. And there are some places that have several planets around it, and each of those are habitable. The TRAPPIST-1 system, discovered a couple of years ago, about 40 light years away, has 7 Earth-like planets. All of them probably have liquid water. Well, actually, the innermost one is probably too high, so they have vapor. But all the others have liquid water. Some of them probably have oceans, at least as deep as the Earth's ocean, if not much deeper. And 4 of them are habitable from the perspective of the dominant form of life on Earth, which is the Extremophiles. What are the most common types of planets? It's interesting. Ice worlds, like we have in our solar system. Europa, Ganymede, Callisto, Titan, Enceladus, Triton, Pluto. These worlds, even bigger ones that are ice-covered oceans, that's the most common type of planet that we're finding. Most life in the universe probably originates in deep oceans. Like on our Earth, it probably evolved in the ocean before it came to land. And on other planets, you probably have a similar type thing. It evolves in the deep ocean before it migrates to land. The story would be different for each planet, but for ice worlds, it would probably migrate through an ice crust before it would get to the top. And there are plenty of examples of extremophiles on Earth that can thrive in that environment. Many types of bacteria, extremophiles called psychrophiles, would be happy in those places. Also, that methane ice worm, that beautiful creature I showed you earlier, that would be quite happy there. That's a common type of planet. Another type of planet is common that is called a water world. Now, this is a planet that's covered with water. Not just no continents. It's water through and through. Well, it probably has a core of rock and metal, but it has an ocean 10,000 kilometers thick. Here's one, GJ 1214b, is a water world. That's the Earth if you put it right at the center of that world. The water represents an ocean that has different layers to it because water at different depths changes phase. So it's a place where the water starts as a vapor, goes to a liquid, goes to a hot ice, goes to a solid ice, goes to a high pressure crystalline ice, goes to something else. There are 11 different phases of water that are known. Each one of those would represent a unique environment for potential life. That's a common type of planet. Probably 5% of all the planets we found are water worlds. There are giant planets like the Earth, but that are rocky, that probably don't have much in the way of oceans. There's one that is 17 times the mass of the Earth. It was nicknamed Godzilla because it was discovered at the time that horrible movie Godzilla came out. Life on Earth that could exist there in a high gravity environment, well, it's probably not going to be you and I. Bacteria wouldn't have a problem, but if I was standing on such a planet and I fell down, it would probably break all the bones in my body. But if I was in an ocean, buoyant, probably be fine. Things like skates would be very happy there. One other type of planet before we move on, rogue planets. You look up, we can't see the stars now. Well, you see a few of them. There's Vega, 11 light years away. But between the stars, there are planets. This is something that was astonishing. There are there are probably many more planets floating around between the stars than there are in orbit around stars. You might think at first blush that those are going to be cold and dead, but nothing could be further from the truth. If you took a planet like Jupiter and its moons and it was shot out into the interstellar medium, not much would change. Jupiter would go on behaving like it does as it is because its energy comes from the interior, and the four large moons that Galileo discovered around it, the ocean worlds, they would stay oceans for billions of years because their energy comes from the interior. They wouldn't change. Unless a planet was really small, being between the stars probably wouldn't change it much at all. So that's really a big change in our viewpoint right there. Most planets don't orbit stars. They float between the stars. Life forms there, well, we'd have to speculate quite extensively for something like that, far beyond my understanding. But it's easy to conceive of life forms like the kind we find in the deep ocean that live at high pressure in cold environments, in environments that you might get close to producing hot ice, and that communicate by either electrical discharges or by fluorescence, like some squids and jellyfish do in the deep oceans of the Earth. They're not dead places. Okay, so exoplanets are ubiquitous. They're incredibly diverse. The Earth-like planets are commonplace, but they're not the dominant form of planet. And the requirements for life are met in virtually all of these environments. Not every environment, but most of them. Also, and I didn't mention this before, some of these planets are Earth-like, they're habitable, they have liquid water, and they've been there for 3 billion years, longer than the Earth has. What would life be like 3 billion years from now on the Earth, which you've got that much time to evolve and change? How do you find life on these planets? We're stuck here on the Earth now. We might make it out into the solar system eventually. Next few centuries, few thousand years, we'll be in the asteroid belt, have cities and countries and out beyond Pluto. But we're stuck here now. We can't get to other stars. How do we search for life there? Well, interestingly enough, we look for the same type of molecules that we found on Venus and that we found on Mars. Phosphine, methane, or other molecules, we call them biosignatures. And that's where the field is right now. We're trying to identify chemicals that would be either proof or highly suggestive of life on these other planets. And it's not easy, it's hard. Okay, I want to wrap up and say just a few words about advanced life. I had my students in my class in the spring send me, each one asked them to send me a picture of what do you think an advanced life would be like. And then I had them vote on which one they preferred, and this came out. The thing is, we don't know what an advanced life form would look like. We would know its history, its story. We wouldn't even know if it is carbon-based like us. But what we can say is that it's in a universe that has the same laws of physics, the same elements, even though it may have vastly increased understanding of science, we're still in the same universe. So when we look at other planets, we can expect to see some of the same kind of things that we see on the Earth, but probably in configurations that we won't understand. What would a super advanced civilization, what would its technology look like? Well, if you look at our cities now and ask the question, what would the pioneers 200 years ago think about our cities today? They probably wouldn't have a clue what they're for, how they worked, what the transportation was. They wouldn't have any idea about communication. They would probably look bizarre, like something like this. They might even, an advanced civilization might even say, gosh, planets are nice. We want to have the same environment that we have on the planet, but we want to travel too to see the rest of the universe. So they'll just take their world with them. And there'll be spaceships that are essentially worlds that they can move. They can move them out of their solar system, and they can travel between the stars. It'll be slow, But if they become immortal, or if they can sleep for long periods of time, they could do that. Probably in a few thousand years, we could do it. With the technology we understand now, of course it's more difficult, we'd have to implement it, but we could start moving asteroids, the moon, and even the Earth. We could move it out of the outer solar system or out of the solar system itself. Because it's not that hard. The laws of physics are going to be the same as they are now. We just need to learn how to harness them. A super advanced civilization might get hard to understand. They might start saying, well, we like stars, so we're going to take our star with us. And that's, that's a little bit beyond our understanding of physics, but that's the kind of thing that you might imagine. If they're highly advanced, thousands, millions, billions of years older than us, still constrained by the laws of physics, but have desires about what they want to do with the universe. And then ultimately, they might even build a shell around their star called a Dyson sphere to harness all the energy from the star for whatever they want to do. And we've seen examples that suggest there may be stuff like that out there. So far, again, no smoking gun, but we have seen examples of observations that look strange. One case came up a couple of years ago when an astronomer was looking at a star. It was looking at a star that one of the planet detecting satellites or spacecraft had found. And they saw unusual brightness variations in the star. And so they said, well, we can't explain this by nature. Maybe this is a mega structure around the star that's being constructed or disassembled by an advanced civilization. Turned out there was a more prosaic explanation. There was a comet, probably a giant comet, that was disintegrating. What about life that's even beyond that? What about life that is very, very different than us? Maybe carbon is as a core element, as a foundation for building long polymers, is not unique. Maybe in different environments where you have magma oceans, maybe silicon is the kind of molecule that life would be based on. And there are plenty of examples of lava oceans, lava worlds around other planets. We don't know how that life form would form or evolve. We don't even know if it could exist. People speculated a lot, but in science fiction, and here's a picture from an episode in Star Trek called Devil in the Dark, where there was a silicon-based life form that was attacking the crew of the Enterprise. It turned out to be rather benign, but it would be able to travel underground by melting rocks with its sort of slug-like residue. We don't know. But one of the things we do know, again, the laws of physics are the same. If you take energy and make it go through a system, let it flow through a system, it generates complexity. When the sun was up, light was coming through the biosphere of the Earth, generating all the atmospheric cycles, the biochemical cycles, the ocean cycles that happen on the Earth, generating complexity. A type of silicon-based life form that is often talked about for the far future is robotics, or robots. Are we going to all replace our bodies with parts that are, non-destructible? This would be a silicon-based life form, but it would be one that we would build. And then there's even possibility of life out there that we fundamentally cannot understand. Again, the same universe, the same laws of physics, but it's so far advanced of us that its desires, its interests, its projects, or its hobbies are just fundamentally non-understandable to us. I mean, if you asked the people that lived on Earth 10,000 years ago to look at us now, they wouldn't understand virtually anything we're doing right now. It would be magic to them. And that's probably the way an advanced civilization will look to us. It will look like magic. So, let's see. Okay, I'll just wrap up. Sorry, I'm running late. Some numbers, some things to think about. Again, the galaxy again. And I was hoping we'd be able to see it, but you really can't. There's Mars. So you're seeing Jupiter and Mars. And if you look just left of Jupiter, that planet is Saturn. It was the first planet I ever saw in my telescope when I was 6 years old. See, they're all in a line. That's the plane of the ecliptic, the plane of our solar system. If you follow that line down about right there, that's the sun. There's the moon. There's Venus. You bring it back up, Uranus and Neptune will be there, and then Mars back over there. That's the plane of our solar system. If you look crossing it is the Milky Way. You can't really see it like, but it would be going in that direction. It's a pretty fabulous place. But our Milky Way is just one tiny bit. It's not even a grain of sand in the universe. With our telescopes, we can look what we call deep into space. The Hubble Space Telescope stared at a place that's really tiny. You take a dime and hold it about 40 feet away. And that's the area of the sky that was looked at for 2 weeks by Hubble. And this is what they saw. That tiny little portion of the sky had over 5,000 galaxies. Some much bigger than our galaxy, the Milky Way, and some smaller. The numbers, I mean, I love big numbers. As a kid, I loved big numbers. But again, it's hard to wrap your mind around them. In our galaxy, 400 billion stars. 11 zeros. If you combine, if you add up, this is an estimate, of course, if you add up all the heartbeats of all the people that have ever lived on Earth, you get a number of about 1 in 20 zeros. If you add up all the grains of sand on Earth, an estimate again, you get about 1 in 22 zeros. Given what we know about the frequency of planets out there, the number of planets, habitable planets, not just planets, is 1 in 24 zeros. So for every single heartbeat of the people that have lived on Earth, there are at least, and this is a lower limit, at least 10,000 habitable planets, defining habitability as habitable for Earth-like life, the dominant form of life on Earth, extremophiles. 10,000 of planets for each single heartbeat. And again, it's a lower limit because we're learning more and we're finding more places where things are complicated than we ever expected. So your homework assignment, I always like to give homework, the next time you're able to see the stars, and you really can't see them well right here, but for every single star you see in the sky, on average, each star is going to have 2 to 4 giant planets. It's going to have, or 2 to 3 giant planets. It's going to have 2 to 4 Earth-sized planets. It's going to have 2 to 5 habitable planets or moons. That's every single star you see in the sky. And again, that's a lower limit. So, thank you. At least you got to see Mars, Saturn, and Jupiter. I was hoping to show you.
We're going to have time for a few questions. I'm going to bring the microphone around. Raise your hand if you have a question. Who has a question? Raise your hand.
I would walk out there, but I'm told to stay in this area right here. I'm in sort of like a jail. If I get out of it, there's feedback, microphone feedback.
Two things. I've never seen Mars that bright. It must be really close.
Yeah, Mars, actually 2 nights ago, Mars was the closest to Earth that it will be for another 15 years.
Okay, wow.
And so that's one of the reasons that's one of the reasons it's very bright tonight.
Not too long ago, we thought there were only about 100 billion stars in the Milky Way.
Could you use the microphone? I can't quite.
Okay.
I will repeat the question.
Okay.
And so now he's got up to 400 billion. Is that a reason?
He's saying that not long ago we said there was only 100 billion stars in the Milky Way galaxy. Now we say there are 400 billion in the Milky Way galaxy. We know more stars over the past time period in the Milky Way galaxy.
Yeah, we're learning more all the time. The problem is we're in the galaxy, in the Milky Way galaxy, and trying to do an inventory of it and see through the stars to the furthest things that we can see. If we were outside looking at it, it would be a piece of cake. But it's hard. To be honest, the numbers sometimes go up and down. They've been as high as 1 trillion, but I've never seen it less than 100 billion. My best guess is something like about 400 billion.
How likely is it that life on Earth originated somewhere else and traveled here on Comet?
Yeah, that's a question that has been thought about a lot. How likely is it? Well, we don't know what the mechanism would be for getting life here, but we have some ideas. For instance, asteroid impacts on Mars throws material into space that sometimes gets in orbit around the sun and hits the Earth. And that's not unusual. There are several hundred meteorites on Earth that we know once were on Mars. We studied those intently because they're pieces of Mars. Some of those meteorites even suggested that they remained habitable while they were in space. In other words, the extremophiles, if they were there, bacteria could survive that transit between the Earth, between Mars and the Earth, even if it took 15 million years. So it's conceivable that you could have transplanted life from Mars to the Earth, because Mars was habitable before the Earth was. It cooled off, and then the Earth cooled off and became habitable. And then Mars, with the catastrophic climate change, and became more desolate like it is now. So it's plausible. Sometimes in my classes I'll say, well, you're all Martians because you came from Mars. Well, but maybe we came from Venus. Venus is closer to the sun. It's a little bit more difficult. But giant asteroid impacts throw lots of debris up into space. If you integrate over time, there's several million tons of Mars rocks that have hit the Earth. Probably less from the Moon, maybe even less from Venus. But it only takes one to contaminate a world with biology and maybe get it to start.
Did it go the other way?
Of course, yeah.
Earth
Life could have formed on Earth and gone to Mars, and then maybe it came back again. I mean, without having some idea of what the mechanism really was, it's hard to be clear, to know more than that. But we do know it's possible.
Well, thank you very much. Thank you.
Yeah, I'm here if you have questions. I'll hang around for a bit.
Here's our homework assignment.
Yeah.
If you were an intelligent being that grew up in the ocean of one of the moons of Saturn or Jupiter, and nobody knew what was beyond that ice coating on the outside of the ocean, and you were the first one to break through and see all the stars, what would it be like in that science fiction story? How would you convince the other members of your society that there was a big universe out there?
That would be like their version of Galileo.
Right.
And people denied what Galileo saw. There were people in the Catholic Church that refused to look through his telescope. He said, I'll show it to you, there are moons going around Jupiter. They refused to look through it. They said it couldn't possibly be true. But eventually, reality is reality. At some point, you can no longer ignore it.
Science. Truth. Thank you so much.
Sure.
Thank you, everybody, for coming.